Okay, so chapter 24, improving performance. All right, so today we are going to learn, not sure why it's cut off the numbers. That's okay. We're gonna talk a little bit about determining when to optimize code, organizing code for optimization, checking for existing solutions, creating simple solutions, and then we'll look into like vectorizing code, avoiding code copying, and then I have an example to evaluate optimizations, using just the t-test as an example. And we'll measure performance using the bench package. Okay, so determining when to optimize code. I have a few thoughts based on some recent work experience that I wanted to mesh with what I think was mentioned in the chapter. So, code that works, generates expected outputs, and is reproducible should be the first priority. What I mean by that, correct, correct code, a code that generates the expected outputs that leads to a good product. Whether that's a model summary or it's a visualization, it's something that's expected. That would be like a good product, regardless of how long it took to make and whatever it is. Um, Incorrect code, regardless of like if it's slow or a memory hog or whatever, and generates a bad product. So if you generate like incorrect outputs, like you did the t-test wrong, or you specified your regression wrong, or made like a bar plot versus a scatter plot. That's like a incorrect output, and that's not expected. You know, um, and so and it can be more nuanced between a good and a bad product, but a good product is way more valuable than a bad product. So if you like basically really fast, which I've done recently, where it's like 300 times faster, and it was great. I loved that, but the product wasn't, it was bad because it wasn't exactly right, didn't match up with the expected output. And so the product was just wasn't good, and because of that, and people didn't find it valuable, to like use it. But even if like things take a long time to load, like we work with a team of different people, who may be coders or not, the non-coders, if like an analysis or something takes time, like it takes like an hour, they will wait. People will use and wait for a valuable product because even if people don't have to like do as much work or there's some other benefits, even if it's slow or a memory hog or whatever, if it still generates a good product, then it's valuable and people will wait and they will use that thing. It's not the case for like a bad product or something that generates something that's incorrect or not totally expected or even just confusing. People will not use it. Like they'll just cross it off the list. And you don't want to spend like hours of your time on something that's just like a little bit off. It's not totally expected. And so then people won't use it. At least it's rubbed me the wrong way in the past. So before you optimize anything, and I know we all love to optimize as coders and people who like efficiency and whatever. Try to avoid that temptation to optimize code that doesn't yet generate a good product. Wait until you make that good product and then optimize from there. And we'll talk about, like using the bench package and other approaches for how can we then, once we have a good product, then optimizing it to make sure it stays a good product. Okay, that's my rant. Sorry about that. Hopefully it's useful. Okay, but optimizing correct code, that should come next. That would be the second priority. And like if you work in whether it's in corporate America or like any like a nonprofit governmental agency, we all have constraints. So everyone has time and space constraints. And these constraints should set optimization goals and priorities. People love to say, don't boil the ocean. And I hate that. But it's kind of true. Like, you don't want to just like optimize, until the cows come home or whatever the phrase is nowadays. Like everyone has their constraints and limitations. And so you just set your goals appropriately so you're not burnt out. We all strive to be efficient, whether doing something in less time or with less space, like memory or, having the computation be like 100 milliseconds less on average. We all kind of like that. I feel like at least for me, it's a little dopamine rush. But I think we need to prioritize ourselves, and we gotta first prioritize to me our various constraints and not overburden or burn ourselves out. Um, again, thanks for listening to my rant. But I think it's important. We can discuss this too. Okay, so now let's say we have good code and it works, it makes a good product. So how can we organize the code for introducing optimizations? So we know so that we know that it's optimized. So like we all, I think, do, we create functions that are repeatable and reusable to evaluate approaches and quantify optimization. And it's important so that you can repeat the code and it's a self-contained and you can really measure that performance gain if it exists. Which means, keep your old functions that you've tried, even the failures, because you never know, like, what the drift is over time, and you may want to go back to what you did before, and it may be valuable to you to make that comparison. So keep your old functions, even the failures. And what helps with this is creating examples with the R-oxygen package where you can have extensive documentation and you can, store your examples within that to auto-generate docs, as well as implement tests with the test that package. So then you can automate like rerunning benchmarks or, having the different functions you made in the past, like is it really the same? You may even want to run it against different operating systems, that may be part of your optimization. And here's like an example if you have two functions, here, and they can sit on single lines where you can think of like having them as separate R scripts and then using a package-ish structure where you can use DevTools load all that would bring your mean1 and mean2 function into your namespace. And then in your oxygen documentation, you can have, creating the vector x, and then you have benchmark, so that you can see that, the mean2 implementation is actually one faster, and actually bench can't access what memory was allocated because sum and length use C primitives. We'll talk more about that in the next couple weeks, but that just means that it's a faster implementation. And I wouldn't have known that without, having these two example functions written, and I could actually see what they are, you know. So keeping them documented, I think is important because maybe down the road you forget which one's better. Right. I made that example. I did that benchmark. Okay. Okay, yeah. So like earlier, there's packages to use that help with making your functions. Also, utilize the use this and DevTools packages for developing and testing functions. Yeah, it's made my life a lot easier. You can use the create package function to make like the project or package directory. That has a standard R folder and description file and has your imports and other things that will allow you to, once you revise your functions within R scripts in the R folder, you can use DevTools load all. That just simulates package loading, to load and use your functions. And then as like test out implementations, do your benchmarks, once you're ready for deployment, then that's when you would, I guess, deploy your package. And like the user would use a library function. DevTools and uses is for when you're developing packages or functionality. It's very useful. Only a couple steps, rinse and repeat. Yeah, it's a great pattern. Okay. Just a note here, and things may have changed with the ubiquitousness of AI tooling and stuff. Online resources and communities like we are in can provide existing solutions or new coding approaches. Um, After exhausting the options at hand that you are aware of, reaching out to online resources like books and, GitHub, like repositories, can provide new approaches not thought of. Like I would never have thought to compute a mean by using sum and length, and like a ratio like that. I would have just used the mean function, but I compute the mean of millions of things every day, and just knowing that it's a different approach, it's faster. I could do my work in less time. That'd be great. Alternatively, reframe the problem to find solutions. This is was a good comment from GitHub online, which I totally agree with, because I've been hearing about and learning about the Arrow package and DuckDB and all that, and I've been wanting to use it. Usually I've just kind of read in data. A lot of the analysts on my team read in data into memory. We all know that's not as efficient. But learning the new pattern, um, changing the paradigm to, establishing a pointer that you can then translate your queries to act against the pointer that's not actually in your session. That's made things both faster and, readable and like more accessible, I guess. Like that reframing, that can really help. So thinking changing how you normally do things could lead to new avenues that that generates a good product. Also, talking to peers helps brainstorm solutions and reframe the problem. Probably a good example of this is the project club in this community. I haven't personally attended, but I see the benefit, of presenting, something you've made or a solution and getting invaluable feedback that can make it like 10 times better. I've done that in other forums and I really appreciate it. Um, and lastly, kind of learning broadly improves your ability to dissect problems and develop solutions. Like even this past week, just learning about rewriting code in C++ and Rust. It's been really that to me is learning broadly, and it's helping me think about, how to attack problems that I have in my kind of day to day. And like even if I'm learning something that is not actionable right now, there's been multiple occasions where something I learned 6 months earlier came into like um relevance at that time. And because it came up, someone voiced the problem in a meeting, and I'm like, hey, I read about that. I know how to do that. Let me, I'll get back to it. So learning broadly, not just in your wheelhouse that you need right now, kind of will help you, like, when the time comes, dissect problems and develop solutions for, like, immediate impact. So it's important. Okay, so strategies for code optimization. We'll go through a couple of these. I'm sure a lot of it is people are aware, but some of these things I was not aware of. Okay, so functions or arguments and data types should factor into code optimization for the problem at hand. So yeah, there's four different tabs here. So an example would be, use vectorization. What does that mean? You're kind of applying the same operation, not element by element, where like that's what the apply is doing. In the benchmark, where you're going by column, and then taking the mean. Whereas the call means function is actually like vectors are applying it across the columns at once. Um, and you can see that it's almost like 20 times faster. Um, so and whenever you have a problem that you can reframe in that way, it can be really advantageous. All right, so please specify your outputs. What that means is that, like I supply, you're not specifying outputs every time you go through a list of vectors or whatever and take the mean. You're reallocating memory every time you go through the list. And so you're making it, storing it, making it again, storing it, and so on and so forth, which can be costly. Whereas the fee apply function, you're already allocating a numeric of length one. So you're just like storing every time you go through the list. So in this benchmark, you see that the time is not too different, but what really matters here is the memory allocation is a lot lower in the free apply implementation than the iSupply. So optimization can not only mean difference in speed, but also in memory efficiency. All right. Oh, also, I'm not looking at the chat. So if there's something good to mention, just interrupt me. Otherwise, we'll just keep going. All right. So another cool strategy is test equally versus by set inclusion. So the any function is faster and allocates less memory than the infix operator. So here you see, like, if I have a vector of what is that, 100 million, elements, and I'm testing for equality to like one number out of 100 million. Um, the any operator actually is a little bit slower, and what I found is depending on the vector size, this changes. So again, making your own functions for your use case is important when determining optimization and that definition for you. But here, like you see, memory allocation is a lot less with the any function than the n fix operator. So again, I'm not sure if on my laptop, my system, the benchmarks were a little bit different, but so I think we can benchmark on the systems that matter where they'll actually be used. And that should help drive what optimization means for your use case. Okay, so the last one, avoiding method dispatch. So here's an example of, I can either use the main function or use the main.default. So instead of dispatching from main, it'll go right to main.default, which can be a little tricky because there may be some like checks in place before dispatch, but it may be helpful in this case. There's marginal optimization. It's a little bit faster, not really. But again, like you see, the vector length is only 1,000. I think if you change into like 1 billion, it might make a difference. So again, depending on your use case, this might be important to look into. Okay, so using vectorized code often leads to optimized code. That's what we saw on the last slide. Acting on the entire vector instead of element by element, which you often will see, and that we already have seen with the implementation with mean, using the ratio of sum and length. Those functions are implemented in C. And they have like they're shown in R. So if anything is really implemented in C, then they're often a lot faster. Most definitely. And we'll talk more about why that is next week, a little bit, and the week after too. So, you'll know it's implementancy if it's using either the dot call or dot internal functions in the body. Anyway, so whenever you look at like functions like call means, you'll see that it's using matrix algebra, and that's implemented in like C internals, and that's a great example of vectorization. Also, like sometimes when you look at the whole page, that could lead you to a vectorized solution. Not all functional pages have this, but some do. So, I think it's important to check out arguments and details and things, the ink out and the optimization. Also performing operations at the scale of your problem shows actual versus expected optimizations. Like we just saw, if I if I avoid method dispatching in the main function for a vector that's 1,000 elements only, and it doesn't matter. The time difference is not that big of a deal. But if my problem called for a billion row data frame, and I calculate the mean on that column vector, it might make a difference. So again, depending on the scope of your problem, um, it might show you the actual versus the expected optimization that applies to you. Okay. Here, okay, so this is an example of, here we're making a random string, and you can, do this in a few different ways. You can create the string on the fly, or again, meaning that you both store it, and then in the next iteration you have to make it again, then store it, make it again, store it, and so on. Whereas you can pre-allocate, you make it once, and then you just store things as you iterate. And that's what you see in this benchmark what like that the back functions are doing. We're using the paste function that involves pre-allocation. And you can see that results in a very large speed up compared to the loop functions, which is collapse. Also, you'll see the memory allocation is a lot lower and can even be invisible to benchmark because it might involve C code. And once computation's out of R, that's when benchmark will be able to quantify memory allocation. So it doesn't mean it's not there. It just can't be measured. Okay. All right, so I think this is the last slide where now I was going through a use case that we have a lot of work. It's not the most sexy thing to optimize or do, but it is there, and this is a good example of applying the different strategies. Okay, so the problem statement, most data analysis projects ask to compare the means between two groups. And often the student's t-test is often asked for. And because it's so simple, and we often have a lot of groups and we do a lot of comparisons, often we have to like thousands or more of these. or even millions, depending on what we're comparing. And so speed can take precedent over safety, given dozens of projects have a similar problem. But correctness is a key requirement. Meaning that we need a good product. It has to be very good. And so the data for this would just be, a matrix with 100 rows and 1,000 columns. You can think of it as 100 people and 1,000 characteristics. And in the bioinformatics space, that can mean 1,000 protein expression measurements or like RNA sequencing or whatever. And like here we could have like two groups, and here just randomly generated with mean 10, standard deviation of 3. But here's what we're going to use for evaluating t-test optimizations. Okay, so here we're going to leverage our different strategies to compute many t-tests. So the base case that we're comparing against is the t.test function. Now, if you just use that interactively, as is, like you loop through every single column and you're getting this to stick, and you just want a vector of all those statistics. This would be in the base case. And you can already probably see where it can be optimized. One optimization to be made is that we're allocating the vector, and then we're constantly overriding it. So we're creating it, storing, remaking, storing, and so on and so forth. So now we can actually not do that. We can use the per package to reallocate on the double vector, but still use the t.test function. And recalling another strategy we had was, instead of like if we know what the inputs are going to be, the arguments are going to be beforehand, and we're pretty sure of it, we can avoid dispatching the ink out performance gains. So this is an example where now we're going to the internal, namespace of the stats package to get out the method used without dispatching. So t.test.default. This might help make things a little bit faster, potentially. Another strategy that we saw was using vectorization or like optimized matrix algebra operations. So here we make a little helper function t_stat, and we're taking the mean length, returning a list, and then applying these operations over the whole vector, like vector of variances or the vector of the groups, and so forth. And we're also pre-allocating already. So we're just kind of building on top of the previous strategies. Well, now that you see that we're using like the mean function, right? That's not as vectorized as it could be. We could be using the internal C implementations. So in the last strategy, we can make it very vectorized, where, we use the call means function, call sums, and square root, to make it very vectorized. But you can see that there's a lot of things being made up front. So that might cause some issues. But we're not really going to know until we have all the strategies in place and then evaluate them on the problem at hand. So until we do that, it sounds good. It sounds like this last one might be the best, but who knows? It depends on what we're going to see in the comparison. So this last slide is just that comparison of these 5 functions. And so we can identify optimal code by our definitions by evaluating the different t-test strategies. And as you can see, like the base case is the slowest. The when we're using per map double the pre-allocation, that's a little bit faster, but it uses like half as much memory. So that's pretty cool. And then like if we're not dispatching, that takes a little bit more speed and maybe a little bit less memory allocation. And then the next one, if we're using matrix algebra, that is much faster, by like 4 times more. And the memory allocation goes down a little bit. But like compared to the base case, memory allocation went down by like more than half. And the speed went down by more than, I don't know, like 4 whatever times. So that would be great. But let's say we're really interested in speed. The vectorize function, that's the fastest. You can see that takes 1 millisecond. However, it, it's eating up memory because we're making a bunch of intermediate objects. So I bet we could find a way to, avoid that memory allocation. But like if you don't care if you're gonna eat up 67 megabytes, then this might be the buzzer, especially if you care about speed and your memory. Like you already have like 16 gigs of RAM, like most people do. So memory allocation is not as big of a problem. But if you wanna like turn out results, then that might be your best bet. But again, depending on your problem and your situation. Okay, so I think, yeah, that's my last slide. Um, so yeah, any questions? Anything you want to go over more? Yeah, anyone's thoughts?
Walking back and forth. It was great to listen to that.
Yeah.
Sorry that I couldn't participate very much. Um, it's uh, definitely like taking the time to benchmark um, is definitely worth it. And profiling, like we talked about before, like finding what's actually slow, because I have definitely optimized things and then realized, oh, it wasn't that slow to begin with. I assumed this would be the problem, but really it's this other thing over here. So.
Mhm. Yeah, right. I spent like a month or two like optimizing where I use like the arrow package to read in data and I use targets and I was being very careful about like how do I use OpenNP and like the memory usage went down by like 50%. Then it was so much faster, like things that took an hour took like 5 minutes, but again, it didn't generate a good it didn't generate a good product. Like the statistics were a little bit off. And I found the issue and I corrected it, but it took me another 3 months. And then that was 3 months people were not using it and giving feedback. So it was detrimental a little bit. And if I could go back, I would have, first made sure things were correct and then optimized, more systematically.
Yeah. Just barely started um, working in C a little bit, and that C or C++ or Rust or any of these solutions can definitely make a much bigger difference than the stuff that we're doing today. But it's definitely a lot harder.
Yeah. But as we'll see next week, it's not totally foreign,
That's true.
but it takes some, you gotta get past some inertia. I have a lot of inertia.
Awesome. All right. Well, as we've discussed, next week we'll see a little bit about C and Rust or C++ and Rust, and
Yeah.
I am looking forward to see how that goes.
Yeah, we got it. Is it okay that I just have one slide? No one slide, just kind of meshed it all together. Is
Uh,
that cool?
yeah, that's fine. No problem. I'll update the table of contents too
Cool.
and make it look better. Cool.
Yeah.
All right. I will see everyone